So my name is Jeremie Dreyfuss. I'm a data scientist for the Advanced Analytics department in Intel. The work I'm going to present today deals with how we use the web text analytics to deliver customer insights. So the Advanced Analytics department's role is a department with over 120 people. Our main goal is to support and bring radical improvement to Intel's critical process. I see it's going to be interesting given that the slides aren't doing so well here. So my apologies if there are some problems. So our key activities, the key activities that we support come from chip design to their manufacturing, and eventually their, the sales process. The team I work on focuses on helping Intel's sales and marketing department, SMG, radically improve their sales process. So in order to understand the work I'm going to present, you have to understand a bit how the sales process works. Intel's customers are divided basically into 10% huge companies. You can think Google, Facebook, name it. It's probably one of our big customers. However, a lot of our revenue still comes from small to average companies. They represent really the very long tail of customers. Because we want to be able to still give them the right sales support, advise them on what are the best product and best product configuration to buy, we need to really understand their business process. If before most of our business was coming from traditional PC resellers, today you can think that a lot of the market has exploded. A lot of Intel's customers do cloud service providing, they do IoT. Their requirements are completely different from the original Intel business. So to be able to support this new sales process, we need to be able to understand who our customers are, what's their business. This is called customer segmentation. A lot of our sales team need access to this customer segmentation. They want to be able to give information in real time to our customers according to their needs. Most of their activities, because we're a global company, would reach regions all around the world in different languages, so we need to be able to support activities in regions that are covered by different languages. And of course, we want to give this segmentation ability to everyone in the sales and marketing organization as a self-service tool. So how do you profile your customers? You can think of looking at the sales information or their behaviors. However, we found that this information was too generic. You cannot understand from someone who's buying a Core i3 if he's going to put it into a tablet for that he's going to sell to a school district, or if he's going to do embed it into a vending machine. So in order to gather more information on our customer, we see how our own customers present themselves to their customers. And to do that, we went and crawled our websites. So we typically crawled about 60,000 websites from our customers, of our customers, and extracted all the textual information and supplied it as a self-service search tool that our sales team could go and pull from. So that could be it, search, and that's it. However, we realized that search is not enough for our sales team. Search is very good at supplying top hit results. You can think the first page of Google search. But what our sales team and marketing team want is all the customers that do smart home in Europe. So here search will fail. What you really are trying to solve is a binary classification problem. You go over all your customer base and you see, do they do smart home or don't they? Okay? So in order to do, we could use the query as a surrogate classifier, if you will, but you know, we all experience the quality of results on the 5th page of Google. It will be rubbish, okay? So what we have to solve is, in order to help our sales team improve the quality of their segmentation results, we allow them to still perform a search query, but then label a few documents. By marking these documents as relevant or irrelevant, we can then solve a straightforward document classification, binary classification, over the textual information that we extracted from these documents. Okay, the slides are improving. Here the query only serves us to then bring the first few documents that the salespeople will be able to label to train our classifier. So let me try and give you a small visualization of the process. Typically, you have your sales agent trying to map. He has a query in mind. He has a segment in mind. He wants these customers, okay? Each plus or minus sign represent a customer or a customer's website. However, queries is not always easy. So, you know, he'll type something. It's approximative. Some of the results will be okay. Some not so much. So by labeling, he's able then to move the net that he's cast to the right area in space. What we did here is that we realized that most of our customers aren't willing to label, you know, more than 5 to 15 documents. When you think of binary classification, you know, you give to someone the task. Here's the document. Label everything, and we'll give you a good classifier. But salespeople are busy people. They have their schedule. They have their needs. They're not willing to do a lot of work, if you may. So what we did here is that we actually also sampled a lot of documents outside their query space to act as a negative class and to make sure that we always have negative documents in our classification scheme. The reason that we have to do this work online every time is that we realize that every salesperson has a different segment in mind. Even if they're looking for a cloud service provider, a few of them, each one is interested in a different aspect of the cloud service provider population. And they sometimes have trouble expressing with words what they're looking for. But however, if you give them a list of customers, they will say, okay, that's good. No, that's not exactly what I'm looking for. So you cannot learn in advance the classification problem. It has to be done in real time, on the spot. So this was, like I just said, we had two major constraints to our classification. One, very little label data. Two, how do you deal with real-time classification of a huge amount of documents? So here's our machine learning workflow. We first considered our website as an ensemble of pages, and we're able to, from there we followed a multiple instance classification scheme where if one of the documents is labeled as positive, then all of the documents are all of the domain is considered as relevant to the segment. In terms of how we represented our documents, we used the standard TF-IDF representation over n-grams. The reason we chose this representation rather than the more fashionable LSTM-based embedding is that up until recently, these methods weren't very good at representing very long documents such as web pages, where you typically have thousands of words. They're very good for short text, reviews, things like that, but not so much for long documents. This is changing today with more method, but not yet. In terms of classification, you have to understand that our users are looking for segments that might be quite rare in our population. 1% of the customers are doing what that sales agent is looking for. So we cannot, we have to keep a very high vocabulary to be able to have the descriptive power over our customers. In terms of classification, we use standard SVM, which is both very good for TF-IDF. If you look at the literature, that's the standard, but more importantly, it's very fast. There are very good implementation in C++. It runs very quickly, and it was very good for our second constraint, which was speed of execution. So I talked about tens of labels, and I talked about tens of thousands, 50,000, 70,000 features. Of course, we're suffering from overfitting. So the question is, how do we deal with this overfitting? Can we still do anything? So there are a few ways to deal with overfitting. The first, you can consider gathering more label data. If you can get access to more data, why not? Second, you can use models that are less prone to overfit to the trained data, more robust. And third, you can simply reduce the number of features in an appropriate way to reduce the noise introduced by rogue feature. So I'm going to go over a few of our experiments in these three methods. So first, data augmentation. Why not add more negative samples? I told you we randomly sample a few documents from outside the query. Why not thousands of documents? So we experimented. Of course, the results are very poor. Why? Because suddenly you have a very unbalanced train set, okay? What we're interested in is the positive class much more than the negative class. But here we have a very strong imbalance. The algorithm isn't very good here. Second, you can think of slowly learning more positive example in a semi-supervised manner. Here it could give very good results. As you can see, the problem with semi-supervision is that you tend to get an improvement in your results the more data you have, but then suddenly you start adding results which don't really follow what you need. And then you have a degradation. So what I'm showing here is what happens when I have an oracle telling me when to stop adding more data. Unfortunately, you don't have this oracle in real scheme, so we had to experiment with another method. What we looked at is bagging. I said adding more negative pages created imbalance. What if I add negative pages but in a balanced manner? Every time I sample new negative samples, train a classifier with my positive samples. I then train a few thousand of classifier and average the results. It's an ensemble method called bagging SVM proposed by Vert and Modlet in 2014. It's pretty standard. It gives very good results. The problem is that it runs fairly slowly. So we couldn't achieve our real-time requirements without a lot of software engineering. But it does give us a very good baseline on what we could achieve. So what's next? Using more robust model. So instead of the regular SVM, why not use SVM with soft margins? You have a penalty where you allow the model to get more training error, but as a counterpart, you have wider margin. The model is less overfitted to your training data. Unfortunately, we didn't see much improvement here. And when we analyzed the result, we realized that this penalty, which you have to find using cross-validation, there isn't good theoretical basis on how to choose this penalty. This penalty is very sensitive to to imbalance in our training data. And here, even if we have imbalance of a few samples here and there, it has a very negative effect on the improvement that you can gain. So our third approach was to look at asymmetric penalty schemes, like in biased SVM, proposed by Liu et al. In 2014. This comes usually from positive and unlabeled schemes. As you can see, we managed to improve our results tremendously. We actually got the same results as with the bagging SVM, but here we got prediction in 100th of the time that the bagging SVM took. Why not, again, add the 1,000 negative sample? You know, I showed you that we know how to deal with imbalanced data. Well, up to a certain point. You still see better results than previously, but we can't achieve, again, the 81% F score. It's F1 score, by the way, the metric that we are looking at. So feature selection. Most of you thought, like, why isn't he doing feature selection straight away? Why am I keeping it till the end? Feature selection actually does work in some cases if you do very extreme feature selection. So we did a few experiments with the chi-square feature selection. It's a very good discriminative feature selection in text. We saw that for segments that you can express with very few words, broad segments, it gives very good results. You know, you keep 5 features and you get good results. And whereas segments that are very narrow in their definition, you need a lot of query words to be able to express them, this feature selection failed. The same way that the query might give good results actually on certain features and poor results on other segments, the same way this feature selection fails. The interesting thing here is that now we have a method from labeled data to have a surrogate for a query. This is something that we actually use later. So what if I told you that we could combine all 3 methods into one method, but not exactly in the way you're thinking? As I explained, we use the query just to get a few labeled, to get the document to label. But actually the query contains a lot of information that we could also use. So why not use the query to act as a surrogate classifier? The query itself, you can think of it as a classifier that gives very noisy label. But you can use these labels to do a first pass of feature selection, meaning that from all your 70,000 features that you originally have, now you can reduce the number of features to only 1,000 features. And these 1,000 features are obtained in a supervised manner, meaning that they're really specific to the segment. So you already have a reduction of your feature space to only 1,000 features. And from there, you can apply the robust modeling that we've presented before. So as you can see, without this feature selection scheme, we had an 81% F1 score. But by first reducing our feature space only to the relevant feature space, we managed to climb up all the way to 90% feature space. So of course, these are average results over a few segments. There is a variability. But as a whole, this method really improved our model's ability. So I basically told you how we solved the problem of overfitting. But if you remember at the beginning, I was mentioning that our customers want segmentation all around the world. Now, they just label documents in English. If I've learned the classification model on English document, how can I use it for documents that are in German, Russian, Polish? So what I'm quickly going to show you is how we solve that problem for them. So imagine that a sales agent is entering a query in Italian, okay? What we're going to do is that we're going to give him a few documents to retrieve. He's going to tag his document. There's going to be a classification in the same way I just described. And now we have about 70 labeled documents, okay? Now what we did is that we took these documents, we simply sent them to a machine translation API to have it translated in all the relevant languages. In our case, it was 8 different languages: French, German, Russian, English, all the documents of relevance. Now, if I were to learn a model just from these labeled documents, I would have poor results. Why? I showed you how the query itself is very important to get good classification results. So you're going to ask me, why not just send the query to the machine translation API? So machine translation are very good at classifying words in context. But if you give them a few disparate words, there's a very big problem of disambiguation. The word education in English, when you translate it into Russian, can have different meaning. It can be education, it can be training, it can be educational, and so on. So how do you deal with this? Our approach was then to use our discovery about harsh feature selection. Basically, we took the translated document, we applied a very harsh feature selection where we kept only the 5 strongest features that are associated with a positive class. And these features acted as our surrogate query that we then applied as a weak classifier with giving us the noisy label to then apply the real feature selection that we're interested in. And this two-step approach allows us then to create eventually the classifier that we wanted in many languages. The reason we use this method and not word embedding method and the like, again, is because if you do joint embedding of word2vec in many languages, the quality of your model depends on the quality you can achieve on word2vec. Unfortunately, we didn't manage to have as good results on word2vec as on the specific TF-IDF models that we had. So this two-step approach did allow us to, again, gain compared to a simple SVM on the translated document, okay? But unfortunately, there's still room to spare. Here you can see, for instance, in German, we had the same segment translated from English to German compared to results obtained if someone was labeling the native German documents. So we still have about 10% margin of improvement in the F1 score. I hope I've convinced you that we've managed to deliver a very valuable solution to our sales team across the globe. Now they're able to do the sales and marketing activity, knowing exactly who they're talking to, what are the customers they're targeting. I showed you that despite complex and harsh overfitting situation, we can still apply from very little labeled data good classification results. And eventually this can be done in a language agnostic way at a very low cost. Because we're using each time translation of very few documents in the machine learning API, the cost of translation is also very low, and the whole system's cost is then kept at a minimum. I'd like to take this opportunity to thank all my team members, Shachar, Tom, and Aran, who also worked with me on this project. Thank you very much. And unfortunately, we don't have more time for questions, but I'm available off stage.